All right, this lesson is looking at simplifying rational expressions. When we simplify rational expressions, we are looking to take a fraction that has some variables in it, and we want to simplify it down as far as we can. To start off, we're going to look at just regular fractions. You should have done this before. You've been learning how to simplify fractions since you were probably in elementary school, and we want to start because it's the exact same concept. Let's look at these first ones. If I asked you to simplify the following, 5 over 15, and number 1 here, if I asked you to simplify that, you would probably just jump in and say, oh, that's 1/3. All right, but why is it 1/3? Why did you go to that conclusion? What is it that led you there? Well, let's look at the pieces and let's break this down as to why that's actually true. Well, you looked at a common factor that was both in 5 and 15. Most of the time, you'd probably say, oh, I could divide by 5 on both top and bottom. And so you divide by 5 on top and bottom. But that's not really what you're doing. You're not really dividing by 5 on top and bottom. That's kind of how we get to our answer. But what's really going on is you're noticing that 5 that you chose to divide by was a common factor inside both 5 and 15. In other words, the number 5 on top could be rewritten as 5 times 1. Over, on the bottom, we've also got a 15 here. It could be rewritten as 5 times 3. All right? And when we look at multiplying fractions, we have always multiplied fractions where we have a over b times c over d, just to give an algebraic example here. That was always a times c over b times d. We always just multiply top times top, bottom times bottom. Using that same idea, 5 times 1 over 5 times 3 pulls apart. It's really 5 over 5 times 1 over 3. And what do we know about 5 over 5? Well, 5 over 5 is 1. The inverse property of multiplication tells us that anytime you have a number over top of itself, it's the inverse property. It cancels out to 1. And also the identity property of multiplication tells us that 1 times anything is itself. And therefore, essentially we have 1 times 1/3 here, and 1 times 1/3 is 1/3. That's what's really going on. Now, you've learned all of that in the process of some shortcuts on how to do it, but you need to understand what's actually happening because we're going to throw some variables in here in a moment, and I want you to see what does and does not work. Let's take a look at 12 over 16. If we identified our common factor, the greatest common factor in 12 and 16, I don't just want to take 2, all right, just like I wouldn't want to take 1. I want to get the greatest one, and I notice the greatest number that goes into both 12 and 16 is 4. 4 goes into both of those. All right. On top, 12 is 4 times 3. On bottom, 16 is 4 times 4. And if we see that, we notice that 4 over 4 makes my giant 1, all right, which will essentially cancel each other out. They're inverses of each other there. And we find that 1 times 3/4 is 3 over 4. And that's why 12/16 reduces to 3/4. What about this example, though? What if I asked you to simplify 7 plus 5 over 7 plus 8? Well, it might be tempting for you to look at this and say, you know what? 7 over 7 is my giant 1 again, and so this reduces down to 5/8. I mean, that's what we were just doing, right? We were pulling out the same thing on top and bottom. But if we actually do our math on this, and we simplify this using our order of operations, I could see that 7 plus 5 is really 12, and 7 plus 8 is really 15, all right? And 12 over 15... if I were to simplify that or reduce it, I see that it's got a common denominator, a common factor of 3 that goes in both of those. This would reduce down to 4/5. And tell me for a second, is 4/5 equal? Let me move my arrow here. Is 4/5 equal to 8/5? Well, no, it is not. They are not equal. They are not the same. And that's showing us that we cannot cancel out the 7s in this one. What makes this problem different from the 2 before, where we were able here to make a giant 1 out of our 4 and our 5 and to remove that in order to simplify? Well, you may have identified the difference is this right here. It's a plus. It is an addition symbol. When we are adding fractions, we can't say that if we have a over b plus c over d, that does not equal a plus c over b plus d. That's not how you add fractions. When you add fractions, we always had to get a common denominator and then separate it out. all right, or put them together. We add the tops and keep the bottoms. So multiplying fractions is different because here you just do top times top, bottom times bottom. That's what allows us to take out these giant ones here because of this multiplication that is in between our two terms, all right, our two numbers up top. But here we've got addition in between it, and it doesn't work the same way. I can't just cancel out those 7s. I can follow my order of operations and add them together and then simplify from there. Or if it was 7 plus 5 over 7 plus 5, those are the exact same numbers, 12 over 12. I'd be able to simplify that. But I can't just cancel when it's separated by addition. So that's one thing we have to consider going into this next problem here. All right, let's take a look if we start throwing in variables. Now, once we throw in a variable, it's no different than when we've been throwing in numbers. Let's separate things out here. Let's look at our numbers first. 6 over 4. How does 6 over 4 reduce? You might be able to see it right away, but let's identify the common factor. The common factor between 6 and 4 is 2. 6 could be rewritten as 3 times 2. And 4 could be rewritten as 2 times 2. What about our x's? Well, our x's are being multiplied by 6, so our x is just being multiplied up top here, and our x is just being multiplied on the bottom here. Everything at this point is separated by multiplication, and therefore I can identify my giant ones. I see I've got my 2's and my x's. Those will both come out as 1's, leaving me with 3 over 2. That's what 6x over 4x reduces to completely. Let's look at the next one. If I've got 3x squared over 9x, let's start with my numbers first. Focus on my numbers first. 3 can be rewritten as 1 times 3, whereas 9 can be rewritten as 3 times 3, noticing a common factor of 3. But what about x? X squared really means x times x. And on the bottom, we only have one of those x's. At this point, everything is separated by multiplication. Let's cancel out my giant ones. I see that 3 over 3 and x over x can come out. And that would leave me with 1 times x up top, which is x. And on the bottom, I've just got a 3 times the 1's, because remember, these are 1's when they cancel out. It's not 0, okay? So as we cancel it out, we get x over 3. And that's what 3x squared over 9x would simplify down to. Let's go to our next example. What if I have x plus 3 over x plus 3? I know I warned you a little bit back. All right, I warned you back in this one right here that we couldn't just cancel out the 7's. All right, and so we have to be careful here. I'm not asking you to just cancel out the x's. That's not what I'm looking at. But I do notice that the group x plus 3 is on top and the group x plus 3 is on bottom. No matter what the value of x is, that will be the same number on top and the same number on bottom. Hence, this becomes a giant 1. It's the same number on top and bottom. Why was this important? This is important because now, after examples 4, 5, and now 6, we notice that you can cancel out 3 things. You can cancel out a number that is the same on both top and bottom when separated by multiplication. We can cancel out a variable that is the same on both top and bottom when separated by multiplication. And we notice that you can cancel out a group that is the same on both top and bottom as long as it's separated from everything else by multiplication. Here, there's nothing else that it needs to be separated from. It's the only thing on top and bottom. Now let's apply that, because this is where we get into simplifying rational expressions. This is a rational expression that we're looking at. It's an expression that is a fraction that includes variables. All right. So in this case here, we do not know the value of x. I can't simplify this by plugging in a value of x and actually figuring out what the number is, but I can simplify it applying what we just learned. Your temptation may be to cancel out 3's or to cancel out one of these x's with one of those x's up top. Or maybe you would try to cancel out with one of these x's here and leave that just as x. But that's not what we're allowed to do, okay? We cannot just cancel things when they're separated by addition and subtraction. I'm just going to bring back the reminder that it didn't work here in example 3. You can't just cancel the 7's here. In the same way, I can't just come down here and start canceling my x's or 3's. I have to get things separated by multiplication. What is the process we learned in order to separate an expression such as this, known as a quadratic, into groups that are separated by multiplication? Well, that is what we call factoring. I want you to factor that top. And if I factor that top, I know it's going to go down to 2 groups. And using our process of factoring, always look to first pull out the GCF. There is no GCF in this case. There's no coefficient in front of x, and there's no x over here. That says no GCF. I also notice this x squared, meaning it's just x squared. It'll come down to x and x. And I just need my x for my diamond problem where I'm looking for two numbers that multiply to get -3, but add to get 2. Well, again, if that top is a negative, that means one's positive and one is negative. And the only factors of 3 are 1 and 3. And hey, look at that. Well, if 3 is positive and 1 is negative, they'll add to get me a positive 2. That gives me x plus 3 and x minus 1. Now, on the bottom here, I see it's x plus 3, but let me do what I did in problem example number 6. I'm going to put parentheses around that entire bottom, making it its own group. You can always put parentheses around the entire top or the entire bottom. That's another way to get them in groups. Now, take a look. These are separated by multiplication. Therefore, these two right here make a giant 1. All right, they would cancel each other out essentially. Whoop, whoop. All right, and therefore 1 times x minus 1 leaves me with just x minus 1 on top, nothing on the bottom. That would be my final expression. Isn't it much easier to deal with x minus 1, all right, instead of this original expression up here? I absolutely agree it is. Now, will this be true for every single number? Will it be true for every single number in the world? Well, let's test that out. Let's pick a few numbers here. All right, if we take the same expression, both on top and bottom, and we evaluate it for any value of x, if we did this correctly, it should be true in both. All right, let's start with 0. What if I take this top one? I'll do 0 squared plus 2 times 0 minus 3 over 0 plus 3. All right, well, I know these give me 0, 0, and minus 3 there up top. So this would go down to -3 over 3. So that whole thing goes down to -1. That's what I get there. Let's test it. In this one right here, I'm going to test this one now, this expression, 0 minus 1, I get -1. Same thing, both of those work. That tells me that these expressions are equivalent when x is 0. Good. Let's test another one just to make sure. It should work for every single number if we did it right. All right, so the next one here, I'll draw a little squiggly line to separate. But I've got 1 squared plus 2 times 1 minus 3 over 1 plus 3. Well, on top here, that's going to give me 1 plus 2 minus 3. Well, 1 plus 2 is 3. 3 minus 3 is 0. And on the bottom, I get 1 plus 3 is 4, and 0 divided by 4 is 0. All right, let's check down below here. What if I do 1 minus 1? I just put 1 in for x. 1 minus 1 is 0. Hey, those are the same. Therefore, it's working. Let's just test one more here. Let's go -3. Make sure you put parentheses around your -3 when you square it. Otherwise, your calculator will tell you the wrong result. All right, but let's just plug all this in. And on the bottom here, I've got -3 plus 3. And let's simplify this. -3 squared is 9. 2 times -3 is -6 minus 3. Okay, in this case, I get 9 minus 6 is 3. 3 minus 3 is 0. All right, so that gives me 0 on top over -3 plus 3 is 0 on the bottom. All right, so I get 0 over 0. All right, and let's test this other one, x minus 1. Well, I get -3 minus 1 gives me -4. I've got a little bit of a problem here. These are not the same. Why did it not work for x equals -3 when it worked for x equals 0 and x equals 1? What was the issue here? Well, something very unique happened. If you notice, our denominator became 0. Remember, you can never have 0 in the denominator of an expression. You can never divide by 0. That's an impossibility in mathematics. Therefore, when we chose a value of x right here that made this expression equal to 0, we ran into an issue. All right? This expression, x squared, looking at the original expression, x squared plus 2x minus 3, can never have a value of x that is equal to 0. How do I know that? Look right down here at the bottom. The denominator is x plus 3. What value of x would make x plus 3 equal to 0? Well, -3 would. All right, if I plug -3 in for x, I get 0. Therefore, we realize that this expression of x squared plus 2x minus 3 over x plus 3 will always simplify to x minus 1 as long as we do not pick a value of x that would make our denominator equal to 0. And therefore, I have to change the way I write my final answer here. when I come back to my work here and I see that x squared plus 2x minus 3 over x plus 3 reduces down to x minus 1, I have to say it reduces to x minus 1 provided that x does not equal what it can't equal. So we would say for x cannot equal negative 3. I would specify that that is the condition upon which that would be met. All right, so I'm just going to erase this part here. I'll put the whole answer in a nice little box. It reduces down to x minus 1 as long as x does not equal negative 3. All right, that's the process. We factor our top, factor our bottom, cancel out our groups, and then state the excluded values of x. Let's put it all together now in our last example here. Simplify the following. If I asked you to simplify 4x squared minus 100 over 4x squared plus 26x plus 30, all right, how would we go about doing that? Once again, you cannot just cancel our x squared, our 4x squared and our 4x squared. That's not allowed. You cannot do that. Do not try to cancel things unless they're in parentheses. We have factored it all out. So let's start by factoring our top and factor our bottom. All right, first thing I notice, my top here has a GCF. 4 goes into everything up top there. All right, 4 goes into 4x squared because 4 times x squared is 4x squared. And 4 goes into 100 because 4 times 25 is 100. And then I notice that I can simplify that further by continuing to factor. So I'm going to factor the entire top here. I notice I have a 4. And then I notice it's just x squared, so it's going to go down to 2 groups with just x. And I also notice that it's not just a just x squared. This one is a difference of squares. If you didn't see that, do your diamond problem and do the negative 25 up top, 0 on bottom. What multiplies to get negative 25 and adds to get 0? Negative 5 and positive 5. All right. So in this case here, I see x minus 5, x plus 5. That's what a difference of squares would have gotten me. 2 different signs, same group, because square root of 25 is 5. Let's look at the bottom here. I see it's also got a GCF of 4, all right, leaving me with x squared plus, oh, sorry, I apologize, it's not 4, all right, it is 2, all right, I see a GCF of 2, and that leaves me with 2x squared plus 13x plus 15, all right, and then this here, I notice it will go down to 2 groups. I know it's going to be 2 times 2 groups here, but I do not know what it is at the moment because it's not a special case. It's 2x squared. I've got to use my diamond problem and generic rectangle. So I'm going to put my 2x squared bottom left. I'm going to put my 15 top right. Multiply those two to get 30. And they have to multiply to get 30, but add to get 13. That's 10 and 3, giving me 10x and 3x. So I pull out the greatest common factor of my rows and columns, giving me plus 5, x, 2x, plus 3. That means that this comes down to 2x plus 3 and x plus 5. All right, so at that point there, I can now simplify by canceling what I see that's a common factor on top and bottom. First off, I see that 2 goes into 4 twice. All right, essentially this was a 2 times 2, and this was a 2 times 1, and I canceled out the 2's, leaving me a 2 over 1. All right, I also see I've got x plus 5 over x plus 5, making a giant 1. And so left on top at this point, I now have this 2 and x minus 5. And on bottom, I've now got this 2x plus 3. And to simplify that all the way down, I have to simplify the top, which is to multiply things back together. All right, I want to multiply things back together here. And in this case here, that would simplify down to 2x minus 10 over 2x plus 3. And we have to state the cases where x cannot equal a certain number. We have to say 4x cannot equal, and we have to look where everywhere there is an x in our denominator. I'm going to look here, and I'm going to look here. What values of x would make those 0? Well, using our zero product property, I know that if 2x plus 3, we don't want it to equal 0. All right, well then I can solve to find what value of x would make that true. Oops, sorry. Divide by 2. And I find that x cannot equal negative 3 halves. That's what I see there. So negative 3 over 2. Again, the opposite of plus 3 is negative 3, and then divide by the coefficient of x, 2. All right, we also see we've got x here in this group right here, x plus 5. What value of x would make x plus 5 equal to 0? Well, that's a little bit easier to see. Negative 5. So therefore, this expression will simplify down to 2x minus 10 over 2x plus 3. All right? Provided that x does not equal negative 3 halves or negative 5.